You probably believe the Earth has a magnetic shield that protects us. And you're right, there is one. But that shield is being torn apart right now, while you watch this video. By the sun. In real time. Not by an asteroid. Not by a geological catastrophe. By the sun. The star we consider benign, that warms us, that makes plants grow. It's attacking our protection with a force most people can't even imagine. And this isn't speculation. It's not science fiction. This is exactly what's been happening in recent months. Events that have left astronomers and infrastructure engineers on edge. In May 2025, a severe geomagnetic storm caused the sun to literally peel away the edge of Earth's magnetic field on the sunward side. In November of the same year, another storm, even more brutal, accelerated solar winds to 1,000 kilometers per second straight into our shield. In January 2026, the largest solar radiation storm in over 20 years swept through the system, impacting GPS, satellites, and power grids across the planet. Here's what's really disturbing. Despite all our technology, despite decades of satellites scattered throughout the magnetosphere, scientists still couldn't see exactly what happens to Earth's magnetic field during these events. They knew the consequences, the GPS blackouts, the low-latitude auroras, the overloaded transformers. But the process itself, the ongoing degradation of our shield, viewed as a global and coherent event, remained invisible. That's about to change. A spacecraft jointly built by the European Space Agency and the Chinese Academy of Sciences is awaiting launch. When it enters orbit for the first time in history, humanity will have a direct view, in X-rays and ultraviolet, of how the sun compresses, tears and erodes Earth's magnetic field during a solar storm. The name of this mission is SMILE, and what it will reveal could completely change how we understand Earth's vulnerability to the sun. To understand what's happening, you need to forget what you think you know about Earth's magnetic field. It's not a metal shell or a solid barrier. It's a dynamic bubble, generated by Earth's liquid iron core spinning and creating colossal electrical currents. These currents generate a magnetic field that extends into space in all directions, what scientists call the magnetosphere. The magnetosphere is not symmetrical. On the side facing the sun, the day side, it extends for about 65,000 kilometers. For reference, that's more than 5 times the diameter of Earth itself. On the night side, facing away from the sun, the solar wind drags the magnetosphere away, forming a long magnetic tail that can stretch for hundreds of thousands of kilometers into space. But the most important part of the magnetosphere, the region where everything that matters for this video happens, is the outer boundary on the day side. It has a name: the magnetopause. Think of the magnetopause as the edge of a pressurized balloon, where Earth's magnetic field meets the solar wind. It's the front line. And contrary to what most people imagine, this boundary isn't static. It's in constant motion, compressing and expanding as the sun changes its pressure. When the sun is relatively calm, the magnetopause maintains a stable position at about 65,000 kilometers from the Earth's surface on the day side. But when the sun hurls a giant cloud of plasma our way, this boundary can be pushed much closer, sometimes dramatically closer. Here's what really matters. The magnetopause isn't just a boundary in space. It's the only barrier between Earth and the constant stream of charged particles the sun launches. If it weakens, compresses, or tears, solar particles penetrate much deeper, hitting satellites, disrupting communications, overloading power grids, and bombarding the upper atmosphere with radiation. The magnetosphere is dynamic. It responds, it moves, and it has limits. Without it, the solar wind would slowly erode Earth's atmosphere. Exactly what happened to Mars, a planet that lost its magnetic field billions of years ago and now has a thin atmosphere and barren surface. The magnetosphere isn't a planetary luxury. It's a fundamental condition for the existence of life as we know it on this planet. If the magnetopause is the only thing standing between Earth and the full force of the solar wind, what happens when the sun decides to push with everything it's got? The sun doesn't stand still. Every second, it launches charged particles into space, protons, electrons, and alpha particles, traveling between 400 and 800 kilometers per second. This is the solar wind. Far from being just a concept, it's a constant, physical flow that travels across the entire solar system and reaches Earth every day. Most of the time, Earth's magnetosphere handles this bombardment well. The magnetic field deflects the particles, forming a turbulent region called the magnetosheath, where the solar wind gets trapped and slows down. The boundary stays compressed yet stable, but the sun doesn't always behave the same way. In certain regions of the solar corona, unstable magnetic structures can suddenly collapse, releasing a colossal amount of energy, plasma, and magnetic field straight into space in a fraction of a second. These events are called coronal mass ejections, or CMEs. A CME isn't just accelerated solar wind. It's a giant cloud of magnetized plasma that can be hurled at speeds of up to 3,000 kilometers per second, reaching Earth in just a day or two. When a CME hits, the pressure it exerts on the magnetopause is drastically higher than normal solar wind, compressing the magnetic field boundary toward Earth and triggering what we call a geomagnetic storm. But there's an even more disturbing process that happens during these storms. A process that goes far beyond simple compression. When the CME's magnetic field points opposite to Earth's field, the field lines can merge, fuse together, in a process called magnetic reconnection. This is where magnetic field lines literally break and reconnect into a new configuration, releasing energy and opening direct channels where solar particles can penetrate the magnetosphere, completely bypassing the boundary that should block them. The alarming part, it's not always slow and controlled. It can become catastrophic. What does catastrophic mean? Exactly, in real and observable terms? First, pure compression. When a CME strikes the magnetopause, plasma pressure pushes the boundary inward, reducing the dayside distance from 65,000 kilometers to a fraction of that. In extreme events, the magnetopause gets pushed below the orbits of geostationary satellites at 36,000 kilometers. Satellites that normally stay protected suddenly face direct solar radiation. Then there's magnetic reconnection on a global scale. When the CME's field aligns opposite to Earth's field, especially when it points strongly south while Earth's points north, reconnection begins, and it doesn't happen at just one spot. It occurs in multiple locations along the magnetopause at the same time. The products of this reconnection have a technical name, flux transfer events, or FTEs. They are temporary channels, magnetic flux tubes crossing the magnetopause, through which solar particles enter directly into the magnetosphere's interior. They act like portals that open and close rapidly during the storm, each one injecting energetic particles straight into the system that was supposed to be protected. During an intense storm, these FTEs multiply and persist for hours. The MMS mission, Magnetospheric Multiscale, detected individual FTEs lasting just minutes, opening and closing in sequence during actual storms. Not theory. Direct measurement. The result isn't permanent destruction. The magnetosphere rebuilds itself when the storm ends. But at the peak, protection drops dramatically. The boundary compresses, tears in multiple spots, and energetic particles penetrate layers they'd normally never reach. This is what shield erosion means in practice. The magnetosphere doesn't disappear completely. The magnetopause gets pushed back, tears in multiple spots, and temporarily can't hold off the solar flux. The real-world consequences are immediate and brutal. Every time these portals open, communication satellites get exposed to energetic particles that degrade circuits. GPS systems guiding planes over oceans start failing. Power grids in high latitudes receive currents that transformers weren't designed to absorb. This isn't theoretical physics, it's destroying the infrastructure that sustains modern life. And then, 2025 happened. In May 2025, a cluster of coronal mass ejections hit Earth in rapid succession. The storm hit G4 level, severe on NOAA's 5-point scale. That means impacts on satellite tracking, severe GPS degradation, possible transformer failures, and radio disruptions. But what the data revealed went beyond the technical impact. Instruments recorded the magnetopause literally pushed inward on the day side. Analyses showed magnetic reconnection happening in multiple locations at once. The shield, literally, was getting peeled away on the side facing the sun. A second storm on June 2nd amplified the effects and prolonged the exposure period. Auroras showed up at latitudes where they never appear. Power grid operators issued warnings for possible surges. GPS systems and satellites reported signal degradation across multiple frequencies. Science was witnessing the consequences, but it still couldn't see the process. In November 2025, the sun wasn't done. Overnight between November 12th and 13th, another high-speed CME struck Earth's field. This time, the solar wind hit 1,000 kilometers per second, one of the highest speeds recorded in decades. G4 level, again. Earth's field compressed hard. Power grids across multiple countries issued alerts. Low Earth orbit satellites faced increased drag. The upper atmosphere expands during storms, increasing friction and forcing operators to adjust orbits. High-frequency communications went down for hours across entire regions. Auroras showed up in Central Europe, the continental US, and latitudes where entire generations had never seen them. Then came January 2026. An X1 9 class solar flare, one of the most intense types, triggered a severe S4 radiation storm, the largest solar radiation event in over 20 years. The consequences hit fast and global. High-frequency radio communications went down in North America, Europe, and regions on Earth's sunlit side. Satellite operators got alerts about increased radiation. Aviation systems on polar routes, where Earth's shield is weaker, had to evaluate route changes. On March 4, 2026, a new G1 storm from a coronal hole is underway right now. The Sun entered its peak activity. The 2025-2026 events proved it. The escalation is real, the consequences are tangible, and Earth's facing intense continuous solar pressure. But here's the crucial fact nobody talks about. Science was blind. Scientists knew the consequences. GPS blackouts, low-latitude auroras, power grid alerts. But what was happening to the magnetopause during these events? That remained invisible. Imagine understanding a hurricane through a single weather buoy. You get precise data from that one spot: pressure, temperature, wind speed. But you've got no idea about the storm's size, how different regions behave at the same time, or how the system moves. That was exactly how science was observing the magnetosphere. How's that possible? With all the satellites, decades of space science, why couldn't we see this directly? Since the 1950s, satellites have been studying Earth's magnetic field and its interaction with the solar wind. Missions like Cluster, MMS, Magnetospheric Multiscale, and Geotail placed multiple instruments in orbit, measuring conditions at different points. But all these instruments take point measurements, one spot at a time. Scientists build models from these measurements. The models are powerful, but they're inferences, not direct observations. There's never been an instrument that can watch the entire magnetopause and see how it deforms during a CME. Nobody's ever created a movie of the solar attack. The boundary compressing, reconnection opening, FTEs multiplying, all at once across the magnetopause. Why? The magnetosphere is massive, stretches tens of thousands of kilometers. No camera can photograph it. It doesn't emit visible light during storms, but it emits something else. When solar plasma penetrates the magnetosheath, the region between the bow shock and magnetopause, ions collide with neutral atoms. This charge exchange releases soft X-ray photons, a glow invisible to human eyes, but measurable with the right instruments. And no space mission has ever been specifically equipped to capture this glow and transform it into global images of the magnetopause at the exact moment the events occur. The charge exchange, ions capturing electrons from neutral atoms, happens exactly where the solar wind and Earth's field collide. The intensity and distribution of soft X-rays directly show the magnetopause's state. Where the boundary compresses, ions penetrate deeper, generating more X-rays. Where reconnection happens, the pattern changes. The magnetopause, invisible to any other tech, becomes mappable in X-rays with the right instrument. Not anymore. The solution to this 60-year gap is being prepared at Kourou in French Guiana. Technical approval came in October 2025. It left Europe in February 2026. Launch window, April 2026. SMILE. Solar Wind Magnetosphere. Ionosphere. Link Explorer. The name says it all. The mission captures the direct connection between the solar assault, the magnetosphere's response, and the ionosphere impact, all at the same time. It's a joint mission between ESA and the Chinese Academy of Sciences. This level of cooperation matters. In space science, international partnerships get complicated. SMILE represents a genuine collaboration between two space superpowers, with teams across multiple countries contributing to instruments, software, and operations. Long road to launch. October 2025. Passed flight qualification and technical acceptance review. February 2026. Left Europe for Kourou. Launch window, April 8, May 7, 2026, using Vega C. But what exactly will SMILE do once it's in orbit? The spacecraft carries 4 instruments, each with a specific and complementary function. First, the SXI, the soft X-ray imager. This is the instrument that makes the mission possible. Remember the charge exchange? Ions colliding with neutral atoms and emitting soft X-rays? The SXI detects this glow and turns it into images, not data points. Global images of the magnetosheath and magnetopause. The magnetic boundary compressed and deformed, mapped as a whole like never before. Think about what this means. We'll finally see an uninterrupted visual record of how Earth's field responds to a CME, where the boundary fails first, where reconnection begins, how FTEs spread, how the system recovers. Second, the UVI, the ultraviolet imager. While the SXI watches the magnetosphere's edge, the UVI points down at Earth's auroral regions. Auroras aren't just beautiful, they're a signal that solar particles are penetrating the field and hitting the polar atmosphere. The UVI records auroras the instant they form, while the SXI maps the magnetopause. Finally, we'll see the complete chain. Solar assault, magnetopause response, ionosphere impact. All connected, all visible at once. Third, the MAG, the onboard magnetometer. While the SXI and UVI capture global images, the MAG measures local field conditions where the spacecraft sits. It provides the precise context to interpret what the images show. Actual field values right where the spacecraft is. Fourth, the LIA, the light ion analyzer. With the MAG, it measures particles in the spacecraft's immediate environment, the data that translates what the SXI images show into actual particles. SMILE's orbit wasn't random. The spacecraft follows a highly elliptical path that keeps it watching the magnetosphere's dayside for up to 40 consecutive hours. Here's why that matters. Geomagnetic storms last 48 hours. With a 40-hour window, SMILE can track an entire storm, from initial impact to recovery, without losing the region of greatest interest. The 40-hour orbit isn't a technical detail, it's a deliberate choice central to the mission. Our unprecedented chance to observe an entire geomagnetic storm cycle with no gaps, no time jumps. Continuous monitoring of one of the most crucial and least understood processes in our space environment. What's SMILE going to see once it's in orbit during the most intense solar peak in 2 decades? When SMILE goes operational, there are 4 types of knowledge we've never had. And they show just how blind we've been. First, the global dynamics of the magnetopause during a CME. Models simulate how the boundary deforms when a CME hits. Solid physics, decades of refinement. But they've never been validated by watching the entire boundary during an event. SMILE will finally compare predictions to reality, showing where the boundary fails first, how much it compresses, how deformation spreads, and how recovery unfolds. Second, where reconnection happens. We know it occurs at the magnetopause. But where exactly? Which regions? What field configurations? What solar wind conditions? That's inferred, not observed. SMILE will map where reconnection starts and how it spreads during real events. This redefines our understanding of how solar particles enter Earth's field, one of space physics' fundamental unsolved problems. Third, the direct link between magnetosphere and ionosphere. With SXI and UVI operating together, we'll finally see both the magnetic boundary's response and the auroral response at the same time. This proves the complete chain of cause and effect. How solar pressure on the magnetopause transfers energy to the polar regions and how fast. We've studied this coupling indirectly for decades. SMILE will watch it directly. Fourth, this one affects you directly. Better storm forecasting. SMILE's data feeds into the models used by satellite operators, power grids, and aviation to protect infrastructure. More accurate models mean earlier warnings, more time to take action, and lower risk of failures that cost billions and impact millions. This tech matters in real life. The 2025-2026 storms proved how vulnerable our infrastructure is to solar activity. The January S4 event, largest in over 20 years, showed the risks aren't theoretical, and timing couldn't be better or worse. The sun's at peak solar cycle 25. Maximum activity, right when SMILE launches. The spacecraft won't wait for storms. It'll find them, probably within days of orbit. Every storm SMILE observes generates new data, not estimates from isolated points. Global images of the magnetopause under real impact. The difference, a model with this data versus without it, is hours of warning versus system failure. It's the difference between grid operators who protect infrastructure and operators who discover the storm when alarms go off. We've spent decades blind during the most dangerous solar period in generations. That is about to change. Forget the magnetosphere as solid shield idea. It's a dynamic, compressible boundary that tears in multiple places during severe storms. Forget that we understand this. 60 years gave us satellites measuring isolated points, models inferring global behavior, and solid physics. But a dynamic visual record, tracking the solar assault the moment it happens, never existed. SMILE isn't a niche mission anymore. It's humanity's first real attempt to see our vulnerability to the sun clearly. Think about what this means. For 60 years, we've built our understanding from fragments. Localized measurements extrapolated into models we could never verify. The models protecting our grids, satellites, and navigation were calibrated with incomplete data. SMILE finally reveals if they're right and where they're wrong. Timing isn't coincidence. The 2025-2026 storms, G4 in May, G4 in November, S4 in January, hit while the mission was finishing. The spacecraft that'll finally reveal the process was getting flight qualified while the sun relentlessly demonstrated the threat, with real consequences. When SMILE launches between April and May 2026 and enters its 40-hour orbit, the sun will probably have another event waiting. The solar peak doesn't wait. When the data arrives, we'll break it down. Subscribe.